Hello and welcome. In this video, we are going to look at optimization problems. So an optimization problem is really just a situation where we're looking at the best way to maximize or minimize a particular situation, the best way to maximize profits or minimize cost or maximize volume or minimize volume for that matter. So optimization just means finding the possible parameters that will create that maximum or minimum situation for a particular problem. That is going to be the focus in this video. We are going to look at quite a few examples, some of them where we're looking at objects and maximizing volume, some of them where we're looking at more math-focused problems where we're looking at two different types of numbers. We're going to look at some problems that involve functions, all kinds of different things to just really get a well-rounded idea on how to approach different optimization problems. So some tips for the process of actually working with these problems are, first, just like when we talked about related rate questions, always draw a picture unless there's one given for you. Label it, identify your variables, define what they are, make sure you have a clear understanding of what the question is asking and how that can be represented. When you're doing this, you're going to write a primary equation that relates your variables together. Sometimes that's going to be something like volume or surface area. Sometimes it'll be clearly defined within the problem. And you're going to isolate whatever is supposed to be maximized or minimized. Then you may need a second equation so that you can rewrite one equation in terms of another. You should consider any domain restrictions for a particular problem. If we're talking about volume or surface area, we obviously can't have a negative value. But after you set up your equation, you're going to take the derivative. You're going to find critical numbers and make a number line and determine what your max or min value is. Then always make sure that you go back and answer the question that is being asked. If it's asking you for dimensions, make sure your answer is the list of the dimensions. If it's asking you for the volume, make sure that that is your answer. So make sure that you answer the question that's being asked in a complete sentence. And let's actually add that as number 6. Now that we've talked through the process of how to think about and approach a problem like this, let's go ahead and jump right in. We have 48 square centimeters of cardboard to make a box with no top. So this portion up here is empty, no top. The box must have a square base. We can see that represented since both of the dimensions of the base are W. What dimensions give us a maximum volume? So let's go ahead and list out what we know. If we know that we have 48 square centimeters of cardboard to make the box, what we know is that our surface area is 48 square centimeters. And thinking about surface area here, that would be the area of the base, which would be W squared, plus the area of the 4 sides going around being added together. And that would be 4, since there are 4 sides, W times H. So I have now an equation, 48 equals W squared plus 4WH. And what we're trying to maximize, so over here, this is my given. What we want is to maximize the volume, and the volume formula would be the area of the base times the height. So the issue that we have here is that I want this right-hand side of the equation to only have one variable. So what I need to do is go back to the equation that I created here, this surface area. Actually, we'll take this one, this surface area equation, and I want to solve for one of those variables so that I can substitute that into this equation and have volume in terms of only one variable. That's going to make my life a lot easier. So if I look at this equation, 48 equals W squared plus 4WH, I want to ask myself which variable would be easier to isolate, and it seems like it would be easier to solve for H here. So let's go ahead and do that. I'm going to move this up top. If I wanted to solve for H, I would take 48 and I would subtract the W squared that's here, and then I would divide that whole thing by 4W, and that's going to give me H, which means I can now rewrite my volume equation, W squared times what we just found H was, 48 minus W squared over 4W. Now, what I want to do with that equation is I want to simplify it as much as possible before I even worry about any of the calculus involved. So go ahead and pause the video and simplify this. So if I distribute that w squared end, I end up, and then I'm actually going to split my fraction into two pieces, 48w squared over 4w. That's going to simplify to just be 12w. Minus w to the fourth over 4w. That's going to simplify to be w to the third over 4, or 1/4 w to the third. So now I have created a volume equation in terms of one variable. What I need to do now is I need to take the derivative with respect to w. So that will give me dv dw, or you could actually, let's just call it v prime, is going to equal, if I take the derivative of 12w, I just get 12. If I take the derivative of 1/4 w to the third, I get 3/4 w squared. So here I have my derivative equation. We know, based on the calculus that we have been learning, that the way to find extrema is to figure out where the derivative is equal to 0. So let's go ahead and set this equal to 0. And then if we isolate, I'm going to get 3w squared. I'm going to rewrite this like this. Then I can multiply both sides by 4, which would give me 48 on the right, and then divide by 3. So that's going to give me w squared equals 16, which would mean that w is plus or minus 4. Now in this particular situation, and up here it had told us, don't forget to think about your domain. In this particular situation, we can't have a negative width of a rectangle or a square. So I'm going to just put on the lower end of my number line for my v prime, I'm going to put 0. And then the critical value we just found within our range is 4. So if I look at what's happening between 0 and 4, like if I plug 1 into my v prime equation, I'm going to get 12 minus 3/4. That's going to be positive. If I plug in something bigger than 4, like 5, I would get 5 squared is 25 times 3 divided by 4. That's going to be bigger than 12, so I'm going to get a minus here. So now I have identified this is going from increasing to decreasing. We have identified that we have a maximum, which is what we were looking for. We were looking for the maximum volume. So we're going to write our complete sentence, which I would have organized my work much nicer on a piece of paper. We're going to write our complete sentence up here. And what we're going to say is the maximum dimensions or the maximum volume occurs when the dimensions are 4 centimeters by 4 centimeters. And then we need to figure out what the height is. So let's actually find the height. If w is 4, then we're going to get 48 minus 4 squared is 16 over 16. So that's going to give us 2. So our sentence is going to be something along the lines of the maximum volume will occur when the dimensions of the box are 4 centimeters by 4 centimeters by 2 centimeters. So there we go. I have written that sentence in the box in the middle. Keep in mind, you should be making sure your work is followable, that readable to someone reading it, which I understand I did not do a great job here. I'm a little restricted on the iPad, but I also need to make sure that I'm answering the question. So with this restriction of 48 square centimeters of cardboard, I identified the surface area equation there. I figured out what it was we wanted to maximize. I rewrote that volume equation in terms of only one variable so that I could take the derivative and set it equal to 0. And then identify any domain restrictions to figure out with our number line if that critical number is a maximum or a minimum. Then we answered the question in a complete sentence. Let's look at another example. The sum of two positive numbers is 30. Find both numbers if the sum of twice the first plus the square of the second number is, and then down below it tells us we're going to maximize and minimize this situation. So let's first just read through this sentence again and write out what we know. The sum of two positive numbers is 30. So let's go ahead and define two variables to represent our first and our second number. So I'm going to let x be my first positive number and y be my second positive number. The first equation they gave us, the first piece of information, is that the sum of these two numbers is 30. So I now have an equation that relates these two variables together. The second part of this problem says, find both numbers if the sum of twice the first, so 2x, plus the square of the second, y squared, is maximized. So I'm going to put max, and I'm going to let that just be represented by the letter m. So we defined our variables, we found our equation that relates them together, and we found the equation that we need to maximize or minimize in this case. So actually I'm going to put max / min. So what I need to do is go back to my second equation, and I need to rewrite this equation in terms of just one variable. So I'm going to go ahead and solve for y. So that's going to give me y equals negative x plus 30. The reason I'm going to do this is because I can now substitute this in to this equation over here. So let's take the equation that we're maximizing or minimizing and substitute in what we know is true for y. Negative x plus 30, and that's being squared, and we're saying that equals m. Before I do any calculus, I want to simplify this out. So if I square this, I'm going to get plus x squared minus 60x plus 900. And then if I combine like terms, x squared, so this equals m, x squared minus 58x plus 900 equals m. So I have one equation with one variable equal to the thing that I'm trying to maximize or minimize. In this case, we're looking for both. Now I'm actually going to take the derivative of that equation with respect to x. So 2x minus 58 is going to equal m prime. Well, if I subtract 58 and divide by 2, if I want to see where this is equal to 0, 0 equals 2x minus 58, I'm going to get that x must be equal to 29. Now, something that's a little odd here is that we only have one critical number, but we're looking for two different situations. That's where we really need to keep in mind the limitations of this problem. So we know that both of the numbers are not, they're actually, this should say non-negative. I apologize for that verbiage. I know that both of the numbers are not smaller than 0. They could be 0. That's why I don't like that I have the word positive typed here. It should say non-negative. So I also know that the largest either of them could be is 30. If one of them is 0, the other one is 30. And we just found that our only critical number here is 29. So I'm going to just cross this off and pretend like it's not here so we have more space. Let's look at what's happening. If I plug something into the derivative like the number 1, I would get something negative. If I plug something in like the number 29.5, I would get something positive. So we can see from our m prime number line that it looks like we have a minimum when x is 29. But let's actually look at the cases here. If x is equal to 29, that would mean that y would have to be 1. And the thing that we're trying to maximize or minimize, m, would be 2 times x plus y squared. So 2 times 29, which is 58, plus 1, which is 59. So here's the first option. X could be 29 and y could be 1. And the m value in this case would be 59. But we have some other options as well. What happens if x is 0? If x is 0, then y would be 30. So then m would be 2 times 0 plus 30 squared, which is 900. And we have a third case. What happens if x is 30? So this is sort of like when we looked at absolute extrema earlier in the unit. We talked about how the endpoints and all critical numbers need to be considered. So if x is 30, then y is 0. So m in this case would be 2 times 30 plus 0 squared. So m would be 60. So we have 3 possible values. We are looking for the largest and the smallest. So the maximum value would be 900, and that happens when the first number is 0 and the second number is 30. So let's go ahead and write a sentence that explains that. The maximum occurs when the first number is 0 and the second number is 30. The minimum occurs, and we actually got this from our number line, the minimum occurs when the first number is 29 and the second number is 1. So we have now answered both of those questions, both cases, where that value, the sum of twice the first plus the square of the second, is both maximized and minimized. Let's look at a couple more examples. All right, a rectangle is bound by the positive x and y axis and the line y equals -1/2 x plus 3. We're trying to maximize that rectangle. What should the length and width of the rectangle be? So the very first thing that I want you to do is draw a picture of what's happening. Actually draw an x and y axis, sketch that line, and then draw an idea of the rectangle that you're talking about so that you can consider what area it is you're thinking about. So pause the video and draw out what's happening in this problem. So here I have my axes. I know that y equals -1/2 x plus 3 has a y-intercept at 0, 3. And the slope is down 1 over 2. Down 1 over 2. I'm going to make this a little bigger. There we go. And then I'm going to connect these three together to get my line. So we're talking about some rectangle being formed by that line and the x and y axis. So we could identify that the area of the rectangle that we're talking about is going to be x times y. And we know that y is defined to be -1/2 x plus 3. So we could rewrite our area formula as x times -1/2 x plus 3. So we could simplify our area formula to be -x squared over 2 plus 3x. This is what we are trying to maximize. So we can take the derivative of this. So that's going to give us, I'm going to call it a prime, is going to equal, if I drop the x squared, the 2 down, I'm going to get -2x over 2, which is just going to be -x plus 3. And if I set that equal to 0 so that I can find the critical numbers, I'm going to get that there's only one critical number, and that's when x is equal to 3. Now, based on this graph, we know that we're looking only in the positive axes, so the smallest we could look at is 0. And if you look at where this intersects with the x-axis, the largest that we could consider is 6. And then our only critical number was 3. If I plug in something to the derivative between 0 and 3, I'm going to get something positive. If I plug in something between 3 and 6, I'm going to get something negative. So we have a maximum situation here. So if x is equal to 3 gives us our max, then what would y be? Well, y, if I plug x equals 3 into this equation, would be -3 over 2x plus 3, which is just going to be 3 over 2, 1.5. So before I write my sentence, I want to make sure that I know what question I'm supposed to be answering on this sentence. What should the length and the width of this rectangle be in order to maximize the area? So go ahead and pause the video and write your sentence. So here we go. The length of the rectangle should be x equals 3, the width y equals 3 over 2 in order to maximize the area of the rectangle. Let's look at one last example. Which point on the graph of y equals the square root of x is closest to the point 0, 5? So again, I'm going to encourage you to pause the video, do a quick sketch of what we're talking about here, and see if you can create the formula that's going to associate these things together. Then unpause the video and see how you did. So here's my picture of what is going on. We're looking at this blue curve, y equals the square root of x, and we're trying to figure out which point on that curve is closest to the point 5, 0. So anytime what we're really talking about is the distance, which means it's hinting to me that I need to use the distance formula. And in case you have forgotten the distance formula is sort of like the Pythagorean theorem. What you're looking at is the square root of x minus the x value that you're looking at. squared plus y minus the y value that you're looking at, quantity squared. So in this case, the x and the y value that we're looking at, we can get from this ordered pair here. So we could rewrite this formula as the square root of x minus 5, quantity squared, plus y minus 0, or y, quantity squared. Now, if you remember with all the other problems that we have worked on so far today, at some point we needed the equation that we were looking to maximize or minimize, we needed that to be in terms of only one variable. So we can't have both an x and a y here. However, what we know is that y is equal to the square root of x, so I can substitute the square root of x in here, which when I square is just going to give me x. So this is going to be, and I'm going to go ahead and multiply this out, x squared minus 10x plus 25. And then if I square the square root of x, I get plus x. So finally, I'm going to have 10x, not 10x. If I add 1 to negative 10, I get negative 9x plus 25. So now I have the equation that I'm going to use to maximize, or in this case, minimize, since we're looking for the point that is closest. In order to take the derivative to make my life a little easier, I'm going to go ahead and rewrite this using rational exponents. And what I'm going to encourage you to do now is pause the video and see if you can work through the rest of this problem on your own. All right, so the next thing that we would do is take the derivative. So d prime is going to be 1/2. We're using the chain rule here, so everything in parentheses stays the same. We decrease the exponent by 1. And then we multiply that by the derivative of the inside, which would be 2x minus 9. I'm going to clean this up. Since I need the critical values, I really want to look at this in a way where I can see what's happening with this function. So that's a little easier to look at. The numerator will be 0, making the fraction 0. 2x minus 9. That'll give us a critical number. So that's going to give us that x is 9/2. And let's go ahead and look at what would make the denominator equal 0. So this would be 0 if x squared minus 9x plus 25 is 0. So if we said x squared minus 9x plus 25, if that's equal to 0, it doesn't factor. So you can either use complete the square or you can use the quadratic formula. So that would be 9 plus or minus the square root of 9 squared is 81 minus 4 times a is 1 times 25 all over 2 times 1. Now, if you notice, the inside of this square root is going to become 81 minus 100, which is a negative number inside the square root. So there's going to be no real solution to this quadratic here, which means the denominator of this fraction will never be 0. So the only critical number that we need to think about is 9/2. So now we can look at our number line. We know this function stops at 0. We can put 9/2 here. We can plug values into our d prime equation to get that this is minus and this is plus, which gives us a minimum, which means we can now write our final answer. Remember, the question is asking us for what point, so what ordered pair is closest to the point 50. So our question should answer that. This is our x-coordinate, which means our y-coordinate, since y is the square root of x, would just be the square root of 9/2. So I'm going to go ahead and write my sentence. So the point 9/2 square root 9/2, or 9/2 3 over the square root of 2, is the point on the line, or on the equation y equals the square root of x, that is closest to the point 50. So recapping what we covered in this video is about optimization. How do we maximize or minimize a particular output given information about the inputs? We first need to choose our variables, define them, draw pictures as needed, write a primary equation, and isolate whatever variable we're trying to maximize or minimize, and make sure that that primary equation only has one variable. So oftentimes, like we had to do in the volume problem, we may have to isolate h or isolate y or x on a particular type of problem. Then you're going to find the derivative and figure out where it's equal to 0 so that we can look at the critical numbers. When you're making your number line, consider the domain. Are there any restrictions that make it non-negative? Anything else you need to consider? And then once you have found those critical numbers and verified that they are in fact a maximum or a minimum, then you need to write your final answer in a complete sentence that answers the question being asked on the problem. Go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.